This is 1960 IMO problem number 1, and here is a view of this problem. We would like to determine all three-digit numbers n. So let's write that down. So we have this three-digit number n, where A, B, C represent the hundreds, the tens, and the units digit, where n satisfies the following two properties. So firstly, 11 divides n. And secondly, n over 11 is the sum of the squares of the digits. So n over 11 is equal to the sum of the squares of the digits. Okay. So we know these two conditions, and that's it. So we need to find the number n. So this would mean that n can be represented as 100a plus 10b plus c, where, well, a, b, c are obviously in the range 0 to 9, so these are digits. In fact, a, because it says a number, a can't be 0 really, but okay, for the time being, let's keep it, where a, b, c are positive integers again. So we have digits from 0 through 9. Okay, so I don't know how to handle the second condition, but I can start by looking into the divisibility by 11 situation. And you guys more or less know the rules of divisibility by 11, so let's explore that. So therefore n, which is this number, I will rather write it in a different way, which you've seen this trick, I assume, before. So I'll write it as 99a, so just last one, plus 11b. I added 1 because I had 1 less, so I had to add back the a, and then I need to subtract the b, and then I have to add back the c. Well, why did I write n in this form? You can easily see why. I can factor out the 11 here, so I have 9a plus b, and I have the second part. Aha! So because n itself is divisible by 11, and the first term obviously is a multiple of 11, it must be that the second term is also a multiple of 11. So let's write that. So this implies that, 11 divides a minus b plus c. But remember that a, b, c are just digits, right? So they are just digits. So, and a and c maximum number they can get is 9 each, so the sum would be 18, short of 22, right? 2 times 0. So therefore we have, well, this just reduces the problem into two cases, right? So we have either this number is equal to 0, or the max it can get would be equal to 11. So next I'll just do a case work based on these two things, and let's quickly do it. So case 1, so let's just do it here. Awesome. So we have case 1. Well, let's start with the 0 case. A minus b plus c is equal to 0. In that case, let's start using this condition, right? In fact, I don't like this condition. Let's write it like this: 11 times a squared plus b squared plus c squared. Okay, so we are in this case, and let me first replace n with this format, which is a nicer format. Obviously the second term, because we are in the case where it's equal to 0, will vanish, so we will be just left with the first one, right? So therefore we have in this first case we have n, which is this number here, but again the second part vanished. So 11 times 9a plus b is equal to 11 times a squared plus b squared plus c squared. Aha! So the 11s just vanish. In fact, I can play with this condition, and b is really a plus c. It's better to substitute a plus c wherever we see the b. So therefore this is equivalent of saying 9a plus, remember, replace b with a plus c. So that's equal to a squared plus, replace it with a plus c squared plus c squared. And now the rest is just algebraically bashing it through all the way to the end. So let's quickly do it. 10a plus c equals, on this side we'll have an a squared here, another a squared, so we'll have 2a squared. and then we'll have a c square here, another c square, so we'll have 2c square, and then finally we have 2ac. Or if you will, we can just factor out the 2 a square plus c square plus ac. Why did we do that? Because we realized the right hand side is divisible by 2. The left hand side must be divisible by 2 as well. Well, the first term is divisible by 2, so therefore so this implies that c itself is also divisible by 2, so it has to be even. So we have an even c here. Now what I will do is I will take this expression and I will express it as a quadratic in A. I can do that, and you know exactly why I'm doing it. You've seen this before, I'm sure. So I have 2a squared on the right side. So let me move everything to the right side. So I continue from that one. So we have everything on the right side. We would have 2a squared. Remember, I'm trying to express it as a quadratic in A. So therefore the a term here is have a coefficient of 2c here, and then I have another minus 10 here, so plus 2c minus 10a, and finally the constant terms would be 2c squared here, 2c squared minus c, that's the constant term, that's equal to 0. Remember that the roots of this quadratic, so the values of the two roots of the for a, they must be a digit, right? So a is a digit, so it should come out as a positive integer, which means the discriminant, so therefore the discriminant of this thing should be a perfect square. The discriminant is a perfect square. It must be a perfect square, right? So let's calculate the discriminant. So the discriminant would be 2c minus 10 square minus 4 times 2 times 2c square minus c. So we want this expression to be a perfect square. So we can yeah, let's just expand it as far as we can and see if we can make it a perfect square. So the first one would have 4c square minus 20 minus 40 more minus 40c plus 100 minus 16c square, I guess, plus 8c. Rearranging it nicely again, we have 100 minus 40c minus 12c square. So this is our discriminant. Remember that c is even, so therefore c is equal to, let's list the values of I'm just creating this imagination box here. So let's list the values of c and the discriminant, and let's see if we can make it a perfect square. So the values of c are 0, 2, 4, 6, and 8. So when c is 0, that works. 100, which is a perfect square. If c is 2, we would get 100 minus 80 minus, ooh, that's too big. Does that make sense? Because 4 times, so we have 100 minus 80 minus 48, which is negative. So the expression will be less than 0 for all the remaining terms, because we have a quadratic which is looking downward. So therefore the only thing which will work will be the value of c being equal to 0. So remember that c is the units digit of our 3-digit number. And now let's go back to our quadratic. So therefore our quadratic, so taking it back from here, we have 2a squared. I don't want to use the quadratic formula, obviously. Well, actually, I already calculated the discriminant. Why not? So the roots would be it would be minus shoot. So I need to calculate it carefully. Okay. Let's just keep the thing. Okay, so we have 2a squared plus. Remember that c is equal to 0, so it's really minus 2a squared minus 10a, and then 0 here, 0 here, so that's it, equal to 0. I don't need to use the quadratic formula really. So that would give me, I can factor out 2a, so I would have a minus 10 here equal to 0. So therefore a is either 0 or a is equal to 10. And oh my, I'm high. So this one is a 5. I was thinking, wait a second, that's not a 3-digit number then. Yeah. A is equal. So that can't work because remember, our number is a 3-digit number, so A can't be really 0. So therefore, the only possibility is A is equal to 5. But remember, in this case, so far we have, okay, so far we have C is equal to 0. Remember from this. A is equal to 5, and easily we can find B, which is A plus C. So therefore, B will come out as 5 again. And that's it. So therefore, our 3-digit number, ABC, is simply equal to 5, 0, 5, 5, 0. That's it. That's the first case. Let's see if the second case leads to a solution as well. So in the second case, we want the second piece to be equal to 11. So A minus B plus C is 11. And we'll pretty much follow the same type of strategy. So we have A minus B plus C is equal to 11. And like I did previously, B therefore is just A plus C minus 11. I'll just go ahead and substitute this information. So therefore, like we did in the previous case, so N, I'm making use of this one, N, which is equal to this whole thing. Obviously the second part is equal to 11, so 11 times this animal here plus 11, and I will also have 11 times the expression. So let's write that. So we have 11 times 9a minus b, 9a plus b, I should say, plus, remember I have an a minus b plus c term, but remember a minus b plus c is just 11. So that should be equal to 11 times a squared plus b squared plus c squared. So we have a squared plus, well, why not? I can start playing with these things. I can replace b squared with this square plus c squared. Let me confirm I didn't mess up here. So 9a plus b, yeah, it's 9a plus b. Okay. Whew. All right, so the 11s cancel out. Yeah, so therefore we have, so this implies we have a 9a plus b plus 1 on the left hand side, and on the right hand side we have, okay, so this part is really messy. Let me do it carefully. A squared plus c squared, the last term. How do I square this? You guys know how to square it. A squared plus c squared plus 121 plus 2 times 2 times ac, and then minus 2 times 11 and the other 2, so which is minus 22a minus 22b. Okay, I hope I didn't mess up, because I usually do mess up. Yeah, I can even substitute the b here with that expression, right? So why not? So I don't have to have an extra line there. So let me go ahead and do that. So it's 9a plus b. So this is 9a plus, replace the b with a plus c minus 11, a plus c minus 11. And then I have a plus 1, and I have this whole animal here. All right, so what do we do next? I can organize nicely, and like I did in the previous case, I will express this whole thing as a quadratic in A as well. So let's do it very carefully. I have a squared here, another a squared, so I have 2a squared. So I have 2a squared, and then how many a terms? I have 2c times a here, minus, so okay, so I have plus, I have a 2c here, I have a minus 22 here, and then I have 10a coming from here, so it's another minus 10. So it's really 2c minus 32a, and finally the constant terms. Okay, so okay, so the c, I have c squared here, so definitely I have 2c squared. And then how about oh, what's this? Oh, that's a C. Ah, what was that? Okay. So I have 2c squared. It didn't mess up so far. I have minus 22c here. I have another minus c here. So it's a minus 23c. And finally, the constant terms, I have 121 on the right. I'll have another plus 10, so it's 131. That would be equal to 0. Remember, this is a quadratic in A, so the roots, remember, are digits from 0 through 9. So therefore, the discriminant, should be a perfect square. So let's do it. So the discriminant of this expression is, oh boy, 2c minus 32 square minus 4 times 2 times this animal over there. Oh boy, this question turned out to be really bashy actually, and we want this whole thing to be a perfect square. Okay, I've come this far, I can go a little bit further. So I have 4c square. Alright, so I don't see any easy way out of here. So 4c square minus 64, 128c, and then plus 32 square. Let me just leave it like this for the time being. Minus 8 minus 16, minus 16c square, minus 8 plus 8, so 8 times 23c, and minus 8, oh boy, minus 8 times 131. Okay, finally, this expression comes out as, let's factor out 4 first of all. That will save me some space here. Okay, so minus 12, so minus 3c square times c square. And then I have, these are my c terms. So I have, when I factor out 4 here, that one will give me 32. I'll have a minus 32 here, so let's make note of that. And then here, 2 times, so I have a 46, so this is 14. 14c plus 14c. And finally, this animal here, which is factoring out the 4, I have 8 times so I have just a minus 6. Okay. Whew. Reduce my casework by just speculating on what the parity of C actually. Yeah, I should have done that earlier. Let me quickly check the parity of C here. I just realized that, just give me a second. So we have an even number here. Well, this term is decidedly even, so therefore this whole thing must be even, right? So we have a 0 here. So this is even, so therefore this whole thing is even. Hey, this is odd, this must be odd, so therefore C is odd. Okay, so C is odd. Why does it help me? Well, it reduces my work a little bit. So C is 1, 3, 5, 7, or 9, and then I'm checking for my delta. Well, it turns out that all these expressions are negative, so let's check for C is equal to 1 first. When C is equal to 1, so this one comes out as 4 times, so minus 3 plus 14 minus 6. Is this a perfect square? I have minus 9 5 times. Yeah, this one is 20. That's not a perfect square. Let's check the next case. 4 times. So if C is 3, 9 minus 27 plus 42 minus 6, 15, cross the fingers, 9 times 4, 36, yes! Okay, let's try one more, 4 times, well, this one will be huge, right? So because when I plug in 5, so I have already a 25, minus 75 here, and then here I have only a 70, and so this one will be negative, and the others will be all negative. So the discriminant here will be less than 0, less than 0, less. So really I have the value for C. Well, the C would be 3. So therefore C is equal to 3. Go back to our quadratic, simplify the quadratic. So therefore this quadratic becomes 2a squared plus C is 3 now. 6 minus 32 is minus 26a. Let's write that down, minus 26a, and then plus I have 9, 18, hold on, 18, 3 times 23 is 69, minus 69, plus 131, What is this equal to? Oh, okay. So this one is just a 62 plus 18 is 80. That's it. So that's just an 80 here. So that's an 80 equal to 0. Almost done, guys. Come on, hang on. So this implies dividing everything across by 2 minus 13a plus 40 equal to 0. Okay, I should be able to factor this out. I don't want to use the quadratic formula. Minus 8 minus 5, yes. Oh, two sub cases. A is equal to 8 or A is equal to 5. Oh boy. So C was 3 already. So therefore B, remember the formula for B. B was A plus C minus 11. So it's really A plus C minus 11. So if we plug in 8, 8 plus 3 minus 11. So that looks legit. And the other case would give me 5 plus 3 minus... Oh, that one is not legit. So this one is less than 0. So that won't work. So therefore B is 0 really. So B is 0 and A is 8. So therefore this case produces a number ABC which is 803. And that's a valid solution too. In fact, you can just quickly, you can check it yourself that it really works. So therefore the two solutions are really, well, from the first case we got 550, and from the second case we get 803, and we are done.